Hi guys, today we will start our topic. So we will start actually interval estimation today. But before that, I would like to give you some information again. Actually, we solved that, but we will repeat it again. Ancillary statistics and bus theorem and how we can use it. So it might help us to generate confidence intervals, and also the hypothesis testing. We might use this property actually. So let's start with that and then continue with the interval estimation. Okay, so let me share my screen. Okay. Okay, so let's start with the definition of ancillary statistic. So you know actually the meaning of sufficient statistic. So sufficient statistic gives us actually has all necessary information to be able to estimate the parameter that is obtained from the sample. So based on the sample information, sufficient statistic has all necessary information to be able to estimate the unknown parameter. But ancillary statistics are the reverse. So they don't have any information regarding the estimation of the unknown parameter. So basically their distribution is independent from the parameter. So because of that, we can understand we have an ancillary statistic or not. So just check the distribution of the statistic. It depends on that specific parameter or not. If it is not, does not, then it's an ancillary statistic for that parameter. So statistic is ancillary if SPDF does not depend on unknown parameter theta. Okay, so it does not have any information about theta. So ancillary that does not have any information, does not have info about, so we cannot use them to be able to estimate unknown parameter theta. So they are just the opposite of sufficient statistics. Okay. So with the Boston theorem, actually, we can use this ancillary statistics and complete sufficient statistics in the same context. So, so basically, we have different definitions also, like first order ancillary, second order ancillary type of things. So first order ancillary means that if the first moment does not depend, first moment of the statistic does not depend on theta, unknown parameter theta, then it is first order ancillary. If it is second order, then second moment does not depend on theta. But if we are saying that our statistic totally ancillary, so its distribution does not depend on theta, so any of the moments of that statistic not depend on theta. So basically, we are using this in normal distribution case. So when we have a normally distributed random variable x with normal theta and variance 1, then we know that distribution of s squared here depends on, actually not directly s squared, but we have to say n minus 1 s squared distributed as chi-square n minus 1, right? Because the variance is 1. So actually this distribution not depend on theta, right? Then this means that this is an ancillary statistic. Okay. Okay, so let's skip that. So how we can use this? We have a Boston theorem. It's a very nice theorem. It makes many calculations very easy. Because of that, we can calculate or show many things difficult, complex things actually. So let's say we have a random variable x with a PDF f of x theta or PMF actually, so it does not, it has to be continuous, it can be discrete also. Okay, so let's say we have statistic tx, and this is given as complete sufficient statistic for theta. I hope you remember the definition of completeness and sufficiency from the previous semester. And then let's say we have Sx, and this is an ancillary statistic, ancillary statistic for theta. Then this theorem tells us that these two statistics are independent from each other. Okay, so Tx and Sx are independent. So this is a very, very nice property. So sometimes we have these two statistics and their distributions. We need to consider their joint distributions. Because of this Bose theorem, if we understand that our Tx is complete sufficient statistic and Sx is ancillary statistic, this means that we can use their marginal distributions. And then the joint distribution of these two will be the multiplication of marginal distributions. So this makes the calculations very easy sometimes. For example, for normal distribution, we are showing that our sample mean and sample variance are independent based on this Bose theorem actually. So using Bose theorem, everything will be very easy actually. Let me see. Yeah. Let's look at this example, normal example first. So let's say we have an IID random sample from normal with mean mu and variance sigma squared. And let's say we assume that sigma squared is known. Okay, so here we know that from previous semester, you can show that, you know, this is an exponential family distribution, and you can easily show that x bar is a complete sufficient statistic for mu. Okay, then basically we can say that then s squared or n minus 1 s squared distributed as chi squared n minus 1. Okay, so here we can say that, again, previously we said that this is an ancillary statistic because it's distribution free from mu. So this means that x bar and s squared are independent by the Bose theorem. Okay. Okay. Let's consider this example also. Let's say we have a two-parameter exponential d from exponential AB. So let's consider the joint PDF. The joint PDF of this random sample of x1 to xn, where a and b are unknown parameters. So we have 1 over b to the n, e to the minus 1 over b, summation xi minus a, I from 1 to a, and xi are greater than or equal to a. So this is joint distribution. Okay, so let's try to write it this way. Okay, so as you can see here, if you remember, here's the complete sufficient statistic for A as the first order statistic, if you remember. Then if we use that fact, and then if we add and subtract here first order statistic. Okay, so let's see what will happen. So summation xi minus x1 here, and we have e to the minus n over b x1 minus a. Okay, and then the first order statistic, or all of them, are greater than these quantities. So here, as you can see, we can write this joint PDF as a multiplication of two different PDFs. One part does not have any A term. One part has a distribution of the first order, the complete sufficient statistic. So here, X1 is a complete sufficient statistic for A. Okay. But then we can say that this summation xi minus x bar, when we consider its distribution, is independent from A. Okay, so then this will be an ancillary statistic for A. Okay, because we can write there the joint PDF as a multiplication of two different PDFs. Okay, so this is the PDF of x1 and the other for the summation xi minus x bar. X1, sorry. Okay, so this distribution is exponential 0 to b. Okay, so we can say that by plus 2 theorem x1 and summation xi minus x bar are independent. Okay, so to be able to find the best estimators, we have to use this one. If you remember, we were using the Raoult-Blackwell theorem and combine this with the Lehmann-Scheffler theorem. So basically, we have to use this information, that everything will be very, very easy. Okay, so regarding this, let me solve one different question. So let's say, so we need to use this information, actually, the Boston theorem. Okay, so let's consider this. So PDF is given as, let's say alpha. We have 1/2 e to the minus x minus alpha over 2, and the range of x depends on alpha. Alpha is greater than 0. So this information is given to us. Okay, do we need to use this? Okay. Okay, so let's say in the first question we have this. So this means that our x vector includes this x1 and x2. Okay, so basically you can see immediately when we look at the form of the PDF here. So f of x alpha is a function of x minus alpha. Okay, and when you look at the range, x minus alpha greater than 0. Okay, so this is a location type distribution. So alpha here is a location parameter. So first of all, we can notice that last week's topic. Okay, so here our question is, basic question is, show that z equals e to the x1, e to the x1 over e to the x2. Okay, and y equals to the maximum of x1 and x2. Okay, are independent. So we need to show that. Okay, so for this type of independence questions, there are two options actually. Basic option, the regular option that you can consider as the joint distribution of, you can consider the joint distribution of z and y, and then show that this can be written as a multiplication of these two. Okay, so if this can be written, they are independent. Okay, or right now you learn that by that Boston theorem, two statistics can be independent from each other. So when you look at this way, actually, so if you can show that one of those statistics is an ancillary statistic and the other is a complete sufficient statistic, it will be enough actually. So you don't have to work with their joint distribution and marginal distributions and show everything. So everything will be very, very easy. So how helpful as also you can see this example actually. Okay, so let's try to write our Z first. So first of all, let's look at the PDF form again. So when we have two random variables, x1 and x2, and if this is the range of x, so basically from that you can see that, okay, is something wrong? Is it maximum or minimum? It should be the minimum. Let me see. Here I wrote as maximum of these two are complete sufficient, but it should be minimum. Sorry, I need to change this to minimum. Okay, so minimum of these two will be, because here you can see that we have x2 as an order statistic, x1 and alpha. So this basically this range shows us that the first order statistic will be a sufficient statistic, so it should be minimum. Sorry. Okay, so then here we can say that with this distribution we can show that the y is a complete sufficient statistic for what was the parameter alpha. Okay, then if we can show that z is an ancillary statistic, so we don't have to do anything, and then just mention the Basel theorem, and then say that these two are independent. Okay, so let's focus on z. So it is e to the x1 over e to the x2. Okay, so we can write this as e to the x1 minus x2. And here we know that we have a location parameter. And when we have a location parameter, the distribution of x minus alpha should be independent of parameter, right? Okay, then if you consider that and subtract alpha from both sides, okay? Okay, so subtract alpha. Okay, so we have e to the x1 minus alpha and e to the x2 minus alpha. Okay, so this means that basically using the fact that we have a location type family and alpha is a location parameter. Okay, so distribution of this part is independent of alpha distribution. And the same here. Of distribution, let me write it. Distribution is independent of alpha because of this location type family thing. Okay, so this means that basically z distributed from V of alpha. This means that z is an ancillary step. So we know that then y is a complete sufficient statistic, z is an ancillary statistic. So we can say that by the Basel theorem, y and z are independent. Okay, so we don't have to work with the joint distributions, marginal distributions. So I didn't do anything actually, as you can see. Okay, so let's consider another example. Okay, so in this example, we have f of x, theta. This is one of my exam questions, actually, previous exam questions. Okay, so theta, x, and infinity. Okay, theta is positive also. Okay, so actually the first part of the question is theta as a location or scale type. Here, as you can see, this is a function of f of x over theta, and look at the PDF also. So 1 x over theta, infinity. So it is a scale type family, scale family PDF. And here, theta is a scale parameter. Okay, so let's focus on the question here. So first of all, let me give another information. So again, here the range of x depends on the parameter theta. So from here and using the definition of completeness and sufficiency, you can show that the first order statistic is a complete sufficient statistic here. Okay. So here, one part of the question is show that y equals nth order statistic. Sorry, nth order statistic over the first order statistic ancillary. Okay, here actually there is a again there is an easiness actually to knowing that this is a scale type family. Instead of finding the distribution of this, so to be able to show that the y is an ancillary, so you have to show that this distribution is free from parameter, right? But to be able to do that, you need to find the joint distribution of x1 and xn, and then you have to do the transformation, and then find the distribution of y and show that it does not depend on theta. But here, they see it a little very easy. So we know that theta is a scale parameter, right? So using that, this means that when we subtract xn by theta, okay, so its distribution is free from theta, and similarly when we consider x1 over theta, so any random variable, basically distribution of the random variable over the parameter, okay, because theta is a scale parameter, distribution of those will be independent from theta. So consider y. Okay, so our y is this one. And consider dividing this each variable by theta here. So everything will be the same. So we will have exactly the same y value. But here we know that this does not depend on theta. This does not depend on theta. So this means that actually, so both numerator and this denominator distributions does not depend on theta. So then this means that y also not depend on theta. Okay, so without doing any of these joint distributions and then doing transformation, we can say that y is an ancillary statistic. Okay, so we have the complete sufficient statistic, we have the ancillary statistic. Okay, part B. Then we can use their independence. So the third, actually this is the second part. My first part was showing that the parameter scale, location or scale parameter, B is this one, and C show that. Okay, expectation of xn over x1 equals to expected xn over expected x1. Actually, some of you may say that, okay, so they are exactly the same, but actually not. Unless they are independent, you cannot write this in this way. So basically, what you can do here, you can only do this. Okay, and then this will be 1 over x1. And if these two are independent from each other, then under the independence, you can only do this if, let me write if independent, because they are not independent actually. If x1 and xn independent, but they are not. So only thing that you can consider is this one, but you can still not write this one. Okay, and this is not equal to expected, sorry, this does not equal to, okay, not equal to 1 over expected x1. So these are all wrong. Okay. Okay, so this part cannot be done. Okay, so then, so you know that this is not correct and cannot use this approach. Then you have to consider some other thing. Okay, so we know that from the first part, x1 is a complete sufficient statistic, and y is an ancillary statistic. So since x1 is a complete sufficient statistic for theta, and y, which is this one, is an ancillary statistic by the theorem. They are independent. They are independent. Okay, so what this means is when we consider the expectation of complete sufficient statistic times the ancillary statistic here, then we can write this as our expectation of complete sufficient statistic and expectation of our ancillary statistic. So these are independent. Because of independence, we can do that. If they are not independent, we cannot do that. Okay, so here, as you can see, this x1 and this x1 immediately cancels out. So there's no problem to write it this way. So what we have here, so expected xn equals to expected x1 and expected xn over expected x1. Okay. So this means that basically then we solve the question expected xn expected x1 equals to, so divide this part by the expected xn, and this is the solution. Okay, so basically we showed this. Okay. So this, knowing that two statistics are ancillary makes everything very easy. Knowing that we have a location family or scale family, we can immediately find parameter-free distributions. So these help us to get solutions in a nicer way, and quickly you can get the solutions. Okay, so let's start our basic topic here, interval estimation. Okay, so interval estimation. So far we focused on the point estimation. But in the point estimation, what we are doing basically, we are trying to find a single value as a value of a theta based on the sample information. So this sample information, when we get one sample, we can get a different single value. When we have a different sample, even though they might be very similar to each other, very close to each other, they will not be exactly the same. So sample to sample, this value will be varied. So we have to consider the variation actually between these different sample approaches. So on the point estimation, of theta, so the inference is a kind of good guess of a single value as the value of theta. Okay, so here we don't have any accuracy associated with it. Okay, so this is a single value, so sample to sample variations are not considered here. Not considered here. So no, not okay. No accuracy associated with it. Okay. So then, how can we incorporate this sample to sample variations into our estimator? So this is basic motivation in the interval estimation. So basically, we may want to know how close we can expect our estimate. Okay, so how close to the original value? So how close we can expect our estimates to be to the true value, true parameter value. Of the parameter. Actually, we don't know the exact value of the parameter, but we can measure this. So here, then we need to discuss the interval estimation to be able to understand this case. Okay, so this interval estimation. Okay. So here, what we are trying to do, we need to specify an interval where our unknown parameter would like to lie. Okay, it contains measure of accuracy through its variance. Okay. So we try to specify an interval in which the unknown parameter theta is likely to lie. Okay, and it contains measure of accuracy through the variance. Okay, so let's look at the definition. Oops, I didn't change the colors. Okay, so let's look at the definition. Okay, so let's say an interval with random endpoints is called a random interval. We are not focusing on the random intervals, we focus on the confidence intervals, okay? But we always find first the random intervals and then convert them to the confidence intervals. Okay, so for example, when we have this type of thing, so when basically we want to find an interval for theta. So in which interval, in range, this theta might lie. With which probability, what probability actually? So we need to find upper and lower bound for our parameter. And let's say we found them as this one. So when we have a random variable in the upper and lower bound, then this will be a random interval. Then we can calculate their probabilities actually. Okay, so let's say we have this. Okay, and then we found this. So this is a random interval with which probability our theta might lie between this upper and lower bound. So we have to consider their probability. And when we calculate it, let's say it is 95%. Okay, so here, this x bar is a random variable. So, and then this means that this interval, 5x bar over 8, and 5x bar over 3, let's say, will be a random interval. Then we can calculate its probability. Random interval that contains true value of theta with probability 0.95. Okay, so if we estimate, let's say we get the sample and we estimate our sample mean as 4. So if we replace the estimate x bar lowercase estimate, then the resulting interval will be just numbers like 2.5 and 6.67 will be 95% confidence intervals. Actually, we use the annotation for confidence interval for theta. Okay, so where this 95% comes? Because we know that with this probability, 0.95 probability, this lower bound and upper bound will contain theta. But when we have a sample version of it, when we calculate x bar as 4, and then we have these numbers actually 2.5 and 6.67. So these are not random variable anymore. But we know that for any random variable, so this probability has to be satisfied. So then we are saying that this is not 95% probability, it's a 95% confidence. So we are 95% confident that our ranges 2.5 and 6.67 may contain our unknown parameter theta. Okay, so when we have a sample, everything will be different. But first of all, when we derive confidence intervals, we start with the random variables, their distributions, and then try to write. And using the distribution of statistics, we found this probability, and then try to write an interval where to make unknown parameter in the middle of the interval, and unknown parameters or random variable parts should be in the upper and lower and upper bound. Okay, so after generating this random interval, then we convert it to a confidence interval like this. So, but this course we will not take any samples, but we assume that when we have a sample, then what will be the confidence interval? Then instead of writing our interval like that, then we will write this as 5x bar over 8 and 5x bar over 3. So this will be a 95% confidence interval for theta. So can you see the difference here? Okay, so this is a random interval because I wrote them. So these are random variables. But right now I changed them with the sample values, estimates. Okay, so they are not random variable anymore. So these are numbers. So when x bar is 4, it's 2.5, for example. Okay, so this will be a confidence interval, not a random interval. Okay, so after this step, you have to write one more step, and then write everything outside of the probability, and then write each random variable as an estimate to make sure that you are giving us a confidence interval. Okay, so another definition. So with these allergies, I cannot read it again. So sorry, I cannot talk properly. Okay, so an interval. Okay, so this is L, x1 to xn, and U, x1 to xn. Here we are using lowercase letters, not random variables. Okay, so this interval is called a 100% confidence interval CI for theta if when we consider the probability of a random interval okay, so x1 to xn is equals to delta, where between 0 and 1. Okay, so if this is the case, okay, then when we replace these random variables with the estimate values, the sample values, then we have a confidence interval, but this will be a random interval. Okay. Okay, then we can also have just the lower limits or upper limits. Sometimes we don't want to look at the upper bound, or our focus point will be our lower bound for the parameters, or the upper bound for the parameters. So we don't care about the other side. So we might just need to construct one-sided limits. So then the observed value. Sometimes finding these are a bit tricky, deriving these, so I have to be careful. So we will see many examples. Is a lower confidence limit, and u x1 to xn, these are dots, is an upper confidence limit, and the probability delta is called confidence coefficient. Or confidence level. Okay, so how confident we are to say that our theta may lie between L and U. Okay, let me see. Okay, so we finish that. Let me see. Okay. Actually, when we write these, what we are saying actually, so when we have probability that our L xn less than or equal to theta equals to delta. So then this L, when we write them as a lowercase letters, will be a one-sided lower 100 delta percent confidence limit for theta. And similarly, we can write this for u as an upper bound. Let's say delta. So this means that, or write it this way, this means that u with the lowercase x's, so with the numbers, will be a one-sided upper 100 delta percent confidence limit for theta. Okay, so these are the proper definitions. Okay. Actually, let me see. Okay, so one simple example. Actually, we will not generate anything right now, so we will see how to generate it. But let's say we have a normally distributed random variable. So you know this from your first grade class, like 156, I guess. So let's say this is known again. Okay, so here we have mu, but we know that the x bar is the best point estimate for the mu. Okay, so it's an unbiased estimator, consistent estimator, remember, sufficient statistic, uniformly minimum variance, unbiased estimator, maximum likelihood estimator, efficient estimator. So we can say of mu. Okay, so it is the very best estimator. So we know the distribution of x bar for normal. So mu and variance equals square over n. I hope you remember it. Then, okay, so we want to generate a confidence interval for mu. Okay, so then we have to consider x bar and we have to create a location. Actually, here mu is a location parameter. So mu free distribution. Okay, then we can construct the confidence interval easily. Okay, so let's try to standardize it. Okay, so z equals x bar minus mu. As you can see, distribution of x bar minus mu, since mu is a location parameter, will be free from mu. It will be normal 0 sigma square over n. So sigma over n square root of n. So it will be standard normal. Okay. Then, so if we want to generate a confidence interval for z, then we can use this information, right? Then we know that we have a standard normal distributed random variables with some probability. We can have a symmetric distributions here, symmetric areas, actually probabilities, and then we can say that our z value is between the calculated z value will be between minus z and plus z values. So usually we are using delta, but when we combine, basically there's a close relationship between confidence intervals and hypothesis testing. So in this case, we can write this delta as 1 minus alpha. So we will see the relation. So you might already know that. So with this, so with equal probabilities in the tail, we can say that this probability is that alpha over 2. So our upper tail probability is alpha over 2. So we can write this as that alpha over 2. Lower tail probability will be again alpha over 2 here. Then we can write this as that alpha over 2. Okay. Then this means that basically our z is between these two cases. So this is a capital Z, let's say. Alpha over 2 and z alpha over 2. When we look at this probability, it will be delta or 1 minus alpha. What is our z? It is x bar minus mu and sigma. So here we assume that sigma is known. Sigma over square root of that. So only unknown thing here as the mu. So we can write this interval in terms of mu. And then obtain that we can have x bar minus z alpha over 2 sigma over square root of n mu x bar plus z alpha over 2 sigma over square root of n. So this is delta or 1 minus alpha. Okay, so this is a random interval, not a confidence interval. Then to be able to write a confidence interval, so 100 delta percent confidence interval for mu will be x bar. So here I wrote a lowercase letter, as you can see, minus z alpha over 2 sigma over square root of n mu lowercase x plus z alpha over 2 sigma over square root of n. So with that we can find this interval. We can find different intervals actually with using different techniques. Okay, so we will see how to identify those. Okay, so let's skip this also. Okay, then okay, so we found this interval. So this is a random interval. Actually, I forgot to write confidence interval here. So this is a confidence interval, but this is a random interval. So for all probabilistic calculations, we need to use random intervals. But as a result, because users will use the sample information, just insert the sampled items here, x bar values. So we have to make sure that these are numeric values, then people can understand, okay, so this is 5, this is 10. Okay, so we use between 5 and 10 with 80% confidence, 90% confidence. Okay. So as I told you, we can generate different confidence intervals for parameters for the same distribution, same parameters. Okay, so then how can we identify our interval will be the best interval? Okay, so we need to answer that, then we will see how to generate the confidence intervals part. So the most important thing in the confidence intervals, okay, so we know that we can find its probability here, like the probability of this event mu's between these two ranges is delta. Okay, so this is a fixed quantity. At the beginning, we decide on this delta or 1 minus alpha term or alpha term. Okay, and then so with this predefined probability or confidence level, then how can I obtain, or how I can know that this gives me the best interval? Okay, so what we mean by best interval actually, so let's say we have this unknown parameter theta. Okay, so we need to find an interval with the same probability. Let's say we have a 95% confidence interval. Let's say with one method we found that we have our theta lower L1, let's say, and theta upper one, obtained it like that. Okay, so we have the same 95% interval here. Let's say with another method that you will learn. Okay, so we found that well, I couldn't change the colors. Okay, so let's say we found that with the same 95% confidence interval, we found this L2 and U2. Okay, so this interval. But these two has the same probability, same confidence. Which one do you prefer? I guess if we are using the same confidence level, then you prefer the smallest length one, okay, because it gives much more information with the same confidence level. Okay, so what we have to consider here, okay, so let me choose a different color. Let me choose this one. So when we consider the length of this one, let's say L1, and length of this one L2, so we prefer that an interval having the lowest confidence interval. Okay, so here we know that, so 95% confidence interval for theta here can be obtained by theta L1 and theta L2 with length L2. Also, we have a 95% confidence interval for theta, which is theta L2. This should be U1, sorry, theta U2 with, so this should be also 1. I'm confused. U1 and 1 with length L2. Okay, so with the same confidence level, and 1 is greater than L2. So this means that the interval with the smallest length give us more precise results. Okay, so the variation is lower in this case with the same confidence level. Okay, so prefer theta L2 and theta U2 as a confidence interval for theta in this example. So the length will be very important. So we can generate our intervals or choose our intervals based on their lengths then. Okay, so the length of the confidence interval will be upper bound minus the lower bound. Okay, so for normal case, basically, our L will be 2 times ZIF over 2 sigma over squared n for normal example. Okay, so then we need to minimize it, okay? So how can we find? So usually one important thing is how we choose this IF over 2 then. Okay, so we can decide on the confidence level. Okay, so this depends on your problem. If you want to make a very small errors, then you can choose alpha level is very small. But if it is not that important, then you can increase it, and let's say you can use 80% confidence limit instead of 99, for example. But how can we choose? How can we decide to use this alpha over 2? Why it's alpha over 3 or alpha over 4? Why we need to use a symmetric Z values? Okay, so here the minimization problem, actually this is an optimization problem. As a result of that, we decide to use this symmetric tail probabilities. So L here is minimized for a given confidence interval. So we assume that this is given to us, confidence level or interval, if alpha is divided equally both sides. Okay, so how this is possible? So we will see that. So our delta equals 1 minus alpha, and then this means that when our delta increases, then our alpha decreases, and this means that our L increases. So this is one relation. So usually in multiple choice questions, this type of thing is asked a lot. So when standard deviation increases, our length also increases, right? You know, and then when sample size decreases, our length increases. So we don't want to have a larger length. Basically, we want to have a smaller length. So to be able to do that, the variation should be small, sample size should be high, and also the confidence limit value should be high also. So small, sorry. Okay, so for a normal distributed random variables, the confidence interval for mu is exact, but for non-normal distributions, we are using central limit theorem. Mainly, we will see that approximate confidence interval concept, and when our sample size is greater than or equal to 30, we can use this normal approach to this approach. Okay, so let's skip this part. Okay. Okay, so when basically sigma square is unknown, we are using T distribution, remember? Okay, so I actually don't want to give these to you. Basically, you know these actually from 56, how to generate things. But okay, so let me focus on this part maybe. Okay. Okay, so basically in this interval, we don't, in the expectation part, we don't have any statistic, okay? So the expected length of this interval will be the same as the length actually, so we don't have any random variable here. zeta alpha over 2 is the table value, sigma is the known parameter, and is the sample size. Okay, so let me do that. So let's say we have sigma unknown case. So we have a normal distribution, normal with mean mu, and now variance sigma square, but it is unknown here. So I hope you remember how to generate a normal distribution here. Again, here we are using Basso theorem actually to be able to generate an interval for actually use the independence of the variables and generate T distribution. How they generate T distribution is like that. Okay, so remember we have x bar term here, mu and sigma over square root of n term. So we know that this is normally distributed for normal distribution. Sorry. Yeah, this is normal distributed. Oops, sorry, with 0, 1. So we have one sigma term right now. So we cannot write immediately confidence interval because in the lower and upper bound we will have the sigma term, which is unknown. So we need to get rid of that one. So you know, actually we are saying that we are replacing sigma by s, and then so distribution will be t, but it's not like that if you remember. So we also use the sample variance here because we need to generate a random distribution. So we have this distribution. We need to get rid of the sigma term here. Then how can we do that? So then considering any other random variable, considering this x bar, important one, and then the ratio of these two will in such a way that the sigma terms will cancel out. So in this case, what we are using, so we are n minus 1 squared over sigma square case. Okay, so we know that this is a chi-square distributed random variable with n minus 1 degrees of freedom. And then, you know, when we generate student t, what we are doing, we are writing in the numerator standard normal distributed case, and then in the denominator in the square root chi-square distributed random variable over sigma square. Okay, so this is sigma square over the degrees of freedom. Oh, okay. So now this sigma square and this sigma square, sigma actually square root sigma will cancel out. This n minus 1, this n minus 1 cancels out, and we will have s over square root of n. Now we know that this is T distributed. Okay, now we can use these in the interval estimation to get a confidence interval for mu. Then write this. Actually, we will have in the middle the T distributed random variable. Okay, upper and lower bound. Again, I will write n minus 1 alpha over 2, but we will see why it should be like that. N minus 1. So let me write it again. Okay, okay, minus t and minus 1 alpha over 2. So this is 1 minus alpha. Then writing everything for mu inside. So we have s over square root of n, t alpha over 2 and minus 1 mu x bar plus s over square root of n, t alpha over 2 and minus 1 equals to 1 minus alpha. So equals to 1 minus alpha. So this is a random interval. Okay, then we can calculate its expected length. Okay, so what is the length of this one? Upper and lower bound is the same. We have minus sign, plus sign, and subtract them. Again, we have 2 times t alpha over 2 and minus 1 s over square root of n. Then we can calculate the expected length of this. So what is the expected length here? So we have 2 times t alpha over 2 and minus 1 over square root of n and expected s. So this is a capital letter, you know. Okay, then we can talk about this expectation. Then what is expected S? Okay, so S, what is the distribution of S? So here, if you remember, we have n minus 1 S squared, sigma squared, distributed as chi squared with n minus 1 degrees of freedom. Okay, so we have to use this, let me see. Okay, yeah. Then we need to find actually the distribution of, using this, we can get that S squared basically distributed as gamma. Let me remember also. So this is a gamma distributed random variable. The second parameter is 2. So this is n minus 1 over 2. So we multiply this gamma by, so this part will not change. So we have 2 sigma square over n minus 1. Okay, so using this basically, then we can find the expectation of S. Okay, so for the cases that we have a gamma distribution with parameters alpha and beta, then expectation of x to the k equals to gamma alpha plus k over gamma alpha beta to the k. So here our k equals to 1 over 2, okay? So then using this fact, expectation of S will be, okay, so our alpha is n minus 1 over 2, okay, and plus 1 over 2, okay, sorry, and gamma n minus 1 over 2, pardon, and our beta value is 2 sigma squared over n minus 1, 1 over 2. Okay, so we will have the expectation as n over 2 gamma n minus 1 over 2 and in square root 2 sigma square over n minus 1. Okay, so we can put that and calculate the expectation here. Let me see. Okay, then our expected L will be this quantity. Where is it? Let me see. So we have 2 times t I over 2 n minus 1 over square root of n, and these things, n minus 1 over 2, 2 sigma square over n minus 1. This is minus 1. Okay, so this will be the expected length. Okay. Okay. Then let me see. So how can we? Okay, so how can we decide on these alpha values? Okay, so let me. So one example regarding that. Okay, so consider again, we have a normal distributed random variable, but in this case, we focus on sigma square. We assume that mu is known. Okay, so we have a random sample, and then each x distributed as normal with mean mu and variance sigma square. Now this part is known, mu is known. Okay, so we want to find a confidence interval for mu. Okay, so confidence interval for sigma square, sorry. Okay, so here we want to use the knowledge that we have about sigma square, what type of distribution. So we know the point estimator. So sigma hat square here is S square, which is summation xi minus x bar whole square divided by n minus 1. So this is the point estimator. Point estimator. of sigma square. Okay, but we want to generate a confidence interval. So right now we didn't start seeing the methods to construct confidence intervals, but I want to give you the information about the length or how we can maximize or minimize the length, how we need to choose the best confidence interval, what should be the properties of that. Okay, so now so we know S square is the point estimator, and we know that using using this, actually we can find that this distribution is chi-square n minus 1. Okay, so basically then we can use the chi-square distribution, but it is, right skewed, not symmetric. Okay, then we need to find some values. Let's say this part is delta, let's say this is 1 alpha. So what should be the values here, and what should be the tail probabilities? Okay, so this part is the important part right now. So if we know that, so let's say we have A here and we have B here, okay, then we can say that probability that this n minus 1 s square over sigma square is between A and B is delta or 1 minus alpha. So what should be the values here to minimize the length? Okay, so then if you know these, basically we can generate an interval like n minus 1 s square divided by B, and we have sigma square here, and we have n minus 1 s square over A. Okay, and this probability is, let's say, 1 minus alpha. Okay, so then what our main question is, what should be the values of A and B to minimize the length of this interval? Okay, so this is an optimization problem, right? So what is the length? First of all, let's find the length. Okay, minimize the, actually, let me say, expected length. Because we don't have the sample information right now. Okay, so upper bound over minus the lower bound. So we have n minus 1 s square over A minus n minus 1 s square over B. Okay, so we want to minimize this expected length. Okay, so expected length equals to, okay, so we have n minus 1 expected s square, and oh, sorry, let me write it this way. Okay, so then expectation of n minus 1 s square A minus n minus 1 s square B. Okay, so we want to minimize this quantity. Okay, so first of all, focus on this probability. Okay, so focus on this part. Then we have okay, so let's write it this way. Probability that we have A n minus 1 s square over sigma square and B. Okay, so we know that this is chi-square distributed. Let's say that this is our Z. Okay, so probability that we have this. This equals to 1 minus alpha. Okay, so writing this in terms of CDF, we have probability of Z less than or equal to B minus probability that Z less than or equal to A equals to 1 minus alpha, right? So let's say this is, let's name it as G, using the distribution of Z at point B. And let's say this is CDF of Z at A. Okay. Okay. Then we have this quantity. Okay. So we want to minimize the length, and we know this. Okay. So we know that GZB minus GZA equals to, let's say, 1 minus alpha. So to minimize L, let's say, so you can choose one of them. A and B are functions of each other, right? These are functions of each other. So there's a relationship between A and B. So we can choose either A or we can choose either B. So we need to minimize B or maximize A, okay? So what is our case here? So writing this, actually, let me write this expected length again. So we will have, we will have an n minus 1 s squared, but let's write it this way. So b minus a times ab times expectation of n minus 1 s squared. Actually, right now, first focus on that expectations. So just, okay, just these quantities. Okay. So this part does not have any thing that should be minimized or maximized. So this part not our optimization problem. So to be able to minimize L, we need to minimize B. Okay. So let's try to get that. So minimize B for this. Okay. And then we have one constraint such that the CDF thing we have. Okay. Okay, so let's divide this part into two parts and consider them together, then combine their things. So let's take the derivative with respect to B. So here we have 1 minus A over 1 minus B. Okay, so this is the chain rule. Remember, A and B are related to each other. They are functions of each other, so we cannot write separately. So we have 1 minus A squared dA over dB plus 1 over B squared, and equate this to 0. So from here, what we get, we have dA over dB equals to A squared over B squared. Okay, so one thing that we have here. Then from here, let's take the derivative of this part with respect to B also. So dZ over dB minus dZA dB, it will be 0. Okay, so let's write this part again. So dZA dA dB, right? Okay, so derivative of the CDF at point B will be the PDF at point B minus, again, the A, and we have dA over dB equal to 0. So now let's combine everything. So here, from here, we know that dA over dB, here A squared over B squared. So write this here, okay? Okay, so this means that we have dB minus GA. So this is the distribution of Z, which is chi-square at point B and A. Remember here, these points actually. Go back. So dA and dB is A squared over B squared. Okay, equated this to 0. So then what we have here is GB times B squared equals to GA times A squared. So we have such a relationship between the values. So this is the PDF of chi squared. This is the PDF of chi squared with n minus 1 where the height of the PDF at point B and A. Okay, so here's how can we decide then, how can we find A and B, the values of A and B. So here the researchers actually make many trials and errors. Okay, so this requires trial, error, and a table value, table of GZ, which is chi-square table basically. And then as a result of this trial and error values, they decided that even for a right skewed distribution, if we choose A and B as I/2, so our expected length will be minimized. Okay, so this is G, not 8. Okay, so when we choose A equals B as I/2, is satisfied, this is true for symmetric distributions also. Because of that, we don't do anything actually immediately. We divide the intervals by I/2, the tail probabilities. So because of this, actually, since we know this, we don't want to calculate again and again. So this choose of the tail probabilities or the delta value confidence level confidence level will be the same, but the tail probability decision is important. So if we just get half and half, then everything will be nice. So this means that expected L is minimized when alpha equals, no, alpha, A equals B over I/2. So this means that when we choose A and B as I/2 here, so here for the chi-square n minus 1, the distribution, so this is I/2. So this point is chi-square I/2 and minus 1 and I/2. So this part, so remember we are always writing the upper tail probabilities to represent them, chi-square and minus 1 over I/2. So our confidence interval, or the first of all, let's write random interval. So n minus 1 capital S square over chi-square n minus 1 minus I/2 sigma square n minus 1 S square over chi-square n minus 1 I/2. Okay, then 101 minus alpha% confidence interval for sigma square will be n minus 1. This is a lowercase s square, chi-square, n minus 1 minus I/2, and n minus 1 lowercase s square, chi-square, n minus 1 I/2. So here you have to think about, actually, after getting these confidence intervals, right now we didn't start it yet, but so consider give numeric values, okay? So consider here n minus 1 and square parts are the same for both ends, but the table values are different. So here when I write chi-square 1 minus I/2 here, actually, this is not correct, right? Because this is smaller value than this one. So I wrote it wrong. So you have to be careful and then think about the values that you write. So it's correct or not. So this will be I/2. This will be 1 minus I/2. So then upper and lower bounds has the, the upper bound is higher than lower bound, and as it should be. Okay, so. Okay, so you can do the similar calculation for any distribution, basically. Okay, so let's start now how we can derive construct confidence intervals are very simple methods. It's based on the type of the parameters, location, scale parameters, not shape. We don't consider the shape parameter in this, just location and scale. And the name of the method is known as pivotal quantity method. Okay, so today we will consider this one and then stop. Okay, so the methods of constructing interval estimators. Okay, so our first method is the pivotal quantity method. Okay, so we are not working with, we will work with some statistics, but basically we will consider a quantity, okay, using, it will be a combination of the parameter and also the statistic, okay. Okay, so let me choose this color. Okay, so let's start with the definition. So if Q, first definition of pivotal quantity, this is Q, okay? So lowercase q is a function of sample random variables and also unknown parameter theta. Because of that, we are naming it as a quantity, not a statistic, because it will be a function of parameter and also a statistic. Is a random variable that is a function only of sample random variables and this unknown theta. Then this Q is called a pivotal quantity. So it will be our pivot basically to generate intervals. And another thing, actually, I have forgot to add one more property of that. So it should be a function of sample random variables and a parameters, and its distribution should be independent of theta. Okay, so its distribution will not depend on any other unknown parameters. So if its distribution does not depend on theta or any other unknown parameters. So if our focus point, if you want to generate a confidence interval for theta, other parameters will be nuisance parameters. Let's say for normal distribution, we have two parameters, both mu and sigma square unknown. We need to find we want to generate a interval for mu, but sigma also unknown. Then sigma square will be our nuisance parameter here, because our focus parameter is mu, nuisance. Okay, so let's look at an example here. So let's say we have a random sample from normal with mean mu and variance 1. Okay, so let's consider one pivotal quantity. Let's say we have Q, which is in square root of n x bar minus theta. This is how we standardize our random variable x bar. Okay, so this is a function of sample random variables because of x bar, right? And theta. Okay, so one property to be a pivotal quantity satisfied. So let's focus on its distribution. So when we look at its distribution, it is 0 and 1 over n, right? So its distribution not depend on any unknown parameters. So this means that Q here is a pivotal quantity. I usually use PQ, okay, to represent pivotal quantity. Okay, so we have a basic theorem, and we will use this theorem to be able to generate confidence intervals using pivotal quantities. So basically, this theorem tells us that when we have certain statistics, and if we know that we have a location or scale or location scale type distributions, how we find the pivotal quantities. So as you can see here, if we have a pivotal quantity, we can easily derive confidence intervals, because we will have a quantity which is a function of both statistic and also parameters, and this distribution does not depend on any parameter. So basically, actually there should be no n here. It should be just one, right? So we can use standard normal table here, and then easy to define upper and lower bound of the pivotal quantity. And then we can write an interval for theta very easily. Okay, so pivotal quantities helps us a lot. But when we have a scale parameters, we cannot use pivotal quantities because this is only for location and scale parameters. Okay, so we have this basic theorem. Okay, so let's again x1 to xn be a random sample from a distribution with PDF. So here we will consider mostly continuous distributions because these location and scale type parameters, I think, only generated for the continuous distributions. For binomial, for Poisson, for negative binomial, for other discrete distributions, we don't have this concept. For theta in the parameter space, and here assume that an MLE, maximum likelihood estimator, or sufficient statistic for theta, which is theta hat, exists. Okay, so here you have to remember how to find an MLE or a sufficient statistic. Okay, so from the previous semester we already deal with these, remember? Okay, so first rule here on the location parameter: if theta is a location parameter, then Q equals to MLE or sufficient statistic minus parameter is a pivotal quantity. Okay, so if theta is a scale parameter, then Q equals theta hat over theta is a pivotal quantity. So you have to remember those. And then we have a location scale type. If theta 1 is a location parameter and theta 2 is a scale parameter, like in the normal case, then so we have to have two pivotal quantities for each distribution, each parameter. So we have theta 1 hat minus theta 1 over. So remember, our estimator should be a function of this unknown parameter only. So because of that, we have to also replace theta 2 here in the denominator. And for the scale parameter, we have these. So these two are pivotal quantities, for theta 1 and theta 2 respectively. Okay. Okay, so here's theta2 is a nuisance parameter for theta1 in the first case. So we need to replace this with the estimator in the denominator. Okay, so these two are MLEs or the sufficient statistics, so you can use both. Okay, so let's focus on this and how can we generate confidence intervals for that. Okay, so what we will do basically here, okay, so this is the end of the theorem that we have. Then what we will do here is first, let me write the steps. One, find a pivotal quantity first, okay, and then find the distribution PDF or CDF of pivotal quantity, okay. Then after that, decide on the lower bound or upper bound, okay. Decide the lower and upper bounds based on the distribution of PQ. Write an interval for theta. Okay, so these are the steps basically. So let's see how we will do that. Okay, so we have a random sample from exponential distribution, be a random sample from exponential theta, where theta is posted. So here, let's write the PDF here. We have 1 over theta e to the minus x over theta, x greater than 0. So this is the scale type distribution, remember. It is 1 over theta f of x over theta format. And here, when we consider x over theta transformation, this PDF not depend on theta. So here, theta is a scale parameter. Okay, so after that, basically, actually, let me write a 0 step. Decide on the type of the parameter location or scale. Okay, so first step done. Then we need to find a pivotal quantity. So our pivotal quantity will be MLE or sufficient statistic minus, not minus. This is the scale parameter, sorry. Theta hat over theta. So we need to find our statistic, MLE or sufficient statistic. So first of all, let's find the MLE. Let's say theta likelihood function 1 over theta to the n e to the minus summation xi over theta e to xi greater than 0. Take the ln to make calculations easier. Then we need to find the value of theta which maximizes the likelihood function. So it's an optimization problem. The theta. Okay, summation xi over theta square equal to 0. And then we found that theta hat equals x bar. So we can take the second derivative and see it's actually maximizing the likelihood or not. But we will see that. Okay. Pardon. Okay, so then our pivotal quantity will be x bar over theta. Okay, then you need to find its distribution. So this is our pivotal quantity. So second step down. Then the third step. Okay, so at this point you have to know the distributions and their relations very well. So here our xi's are exponential distributed, right? Then this is actually one form of gamma distribution, remember? with 1 and theta. So summation of xi's will be then what? Gamma, right? When we have a random variables or random sample. So we are summing n of them. Okay. Then x bar. We are dividing summation xi by n. So this affects the second parameter, scale parameter. So we have n theta over n. Okay, so we know we found actually, let's find the pivotal quantity, distribution of the pivotal quantity then, x bar over theta, gamma. Actually, this is again, affects the scale parameter. As you can see, okay, so we have a pivotal quantity, its distribution does not depend on theta. Okay, so we can work with this one actually. So no problem with working with gamma and 1 over n. But you know, gamma distribution, we don't have any statistical tables for gamma distribution. So to make the interval readily usable, we have to use, if possible, we have to use the values that can be found from the statistical tables very easily. Okay, so it should be user friendly. This is not user friendly right now, gamma n and 1 over n. So how any user can find this value. Okay, so what we have to do, okay, so we know that gamma distribution is closely related with the chi-square distribution, where the chi-square distribution has statistical tables. We can easily convert this pivotal quantity, and still it will be a pivotal quantity, but its distribution will be chi-square, and then anybody that wants to get the values from chi-square table very easily. Okay, so how can we convert this Q to a chi-square distributed random variable? If you remember, if we can consider, if we change actually the scale parameter of this to 2, then we will have a chi-square distributed random variable. How can we do that? We know that when we multiply a gamma distributed random variable with a constant, then it will only affect the scale parameter, the second parameter we have. So to make this, the scale parameter 1 over n 2, so we have to multiply our q by 2n, right? So if I multiply our q by 2n q, okay, so 2n x bar over theta. So this will be gamma n and 2. So basically, this is chi-square with 2n degrees of freedom. So multiply these two parameters. Okay, so now any users can find the table values of chi-square and easily define it. And as you can see, this 2n q is still a pivotal quantity because it's a function of some random variable and unknown parameter theta, and this distribution does not depend on theta. So it's still a pivotal quantity. Okay, so still pivotal quantity. Okay, then. Okay, so the third step is finding the upper and lower bound. So consider probability of this. So we have 2n x bar over theta, our pivotal quantity. So we want that this probability will be 1 over alpha. And from this, actually, for chi-square distributed random variable, for normal distribution, we already showed that, but it is similar. So you can try and show that if we use the equal tail probabilities, we will minimize the expected length. Okay, so we're using chi-square 2n upper bound and chi-square 2n lower bound. Okay, so then after this, only thing that we need to do is write this interval for theta only. So do a little mathematical calculation. Actually, you don't have to do very difficult job to do that. So we have 2n x bar. Okay, so here's theta and pivotal quantity is negatively related to each other. So upper bound for 2n x bar over theta will be a lower bound for the theta boundary. So theta here, 2n x bar chi-square 2n 1 minus alpha over 2. Okay. Okay. So this is not a confidence interval. So this is a random interval. To write a confidence interval, 100 1 minus percent confidence interval for theta will be, okay, so what we have to do, just replace random variable x bar to an estimate, okay, write everything outside of the probability, and then we have chi-square to an upper bound, oops, y to n, okay, it should be alpha over 2 and 2n x bar over chi-square 2n 1 minus alpha over 2. So this will be our confidence interval that we generate from pivotal quantity. Okay, so let's also write this way. So you can totally write this for the gamma PDF, but when you turn it to, if possible, always try to convert your pivotal quantities distributions to a known one, if possible. So for this case, it was very easy. So we know that we have a very close relationship between gamma and chi-square, and we have a table, statistical tables for chi-square, then we convert it. Okay, so if possible, do that. Also, let's say you want to find a one-sided confidence interval. So this is a kind of a tricky one. So let's say 100 1 minus alpha percent lower confidence level for limit, not level, confidence limit for theta. Here, actually, knowing this is easy because you can get the lower bound. But let's say we didn't calculate anything, but we started with dq. Okay, so we have x bar over theta case. Okay, so we want to find the confidence interval, and actually from that we know that 2n x bar over theta distributed as chi-square 2n. So we have this information right now, and we want to generate a lower bound for theta. Okay, so with 1 minus alpha confidence level. Okay, so how can we do that? So here, when we look at the form of 2n x bar over theta is a how to say, is a negative relationship with theta. Okay, so inverse relationship with theta. So this means that when we want to find not upper, lower, a lower bound for theta, we need to start with an upper bound for 2n x bar over theta. Okay, because pivotal quantity has a reverse relationship between theta. So when we want to write theta alone in the interval, then everything will be reversed. Then we need to start with an upper bound for pivotal quantity and end up with the lower bound for theta. Okay, so in the probability case, we need to consider an upper bound for theta to be able to end up with the lower bound for theta. Okay, so we have to consider chi-square 2n. Right now, upper bound is alpha, not alpha over 2. So because we don't have a lower bound here, so just one bound. So this equals to 1 minus alpha. Otherwise, this will be 1 minus alpha over 2. So be careful about that. And when we write this alone, then we will have, okay, so try to get a lower bound. So we will have 2n x bar over. As you can see immediately, we get the lower bound for theta, not an upper bound. So if you write it this way, we will other way around, then we will get the upper bound for theta. So again, this is a random interval, and confidence lower confidence limit for theta will be 2n x bar over chi-square 2n alpha. So don't forget to write this step. Okay, so after writing this step, please write this. Otherwise, I will get your some points. Okay. 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 So we already talked about that. Okay. Let's see. Okay, so let me stop here. So I will continue to solve different questions, maybe in the class also on Wednesday, and also the station. You will solve many questions regarding this to understand the concept better. So I just want to give one example and stop right now. That will be too much, I think, for you to follow the course. So see you on Wednesday. Please don't forget to follow H5P version of the notes. Also, there will be some questions that you need to answer, and you get credit from that one. So it will be immediately goes to your grades button. Okay, so see you. Bye bye. So let me go back to my Zoom and then stop recording. So see you guys. Bye bye.